So a couple of things that you need to remember from grade 10 are the difference between a relation and a function. So a relation just describes the relationship between two variables, usually our x and our y, but a function's really specific. Every function is a relation, but the function gets more specific. It has one unique y value for every x value, and it passes that vertical line test. So that was that. So every function is a relation. Relations are like kind of the general category, and then we add a rule on for the function, so it gets more specific. Okay, so implicit versus explicit definitions. An implicit definition, which is what we're doing today, is an indirect definition for the value of y in terms of x. Essentially, the dependent variable is not isolated to one side. So if we look at this, the y isn't isolated to one side, it's kind of built in. These two things are happening together. Explicit is when it's nice and easy. We've done these ones. This is what our whole unit has been on. So this is y equal. So implicit, x and y are together on the same side. Explicit, y is isolated. And that's been really easy for us to do. So here's an implicit function. Okay, so all it is the explicit one of it is we're isolating the y value, dividing everything by 3, moving all the other things other than y to the same side. So these are the same equations. We're just isolating the variable y. Implicit, explicit. So here, what is this going to give us? This is going to give us a really ugly parabola. Well, not an ugly parabola, but it would have fractions in it. So this is going to give us a parabola. We know that it's a function. It will pass the vertical line test. This one here is implicit because the y is mixed in with the x. This is going to give us a circle. Maybe an ellipse. Might give us an ellipse. You know what a circle is? You know what a hyperbola is? Are they the same thing? No. So this is going to give us a circle or an ellipse. I feel like it's going to give us a circle. So if we were to rearrange it, we know that we're going to have two kind of parts. We're going to have that positive principal root and that negative root as well. So there's going to be more than one value. It will not pass the vertical line test. That's why it's a relation. So this is a D3 question. Easiest thing to do is change it from implicit to explicit. Easiest thing to do. So we're going to have y equals negative x squared plus 2x plus 4. So this one and that's your explicit. So implicit, the x and the y are together on the same side. Explicit, now that it's rearranged like that, doing the derivative is super easy. We're going to use our rules from D3. Right? Easy peasy. And I think that's how we would tackle any of these that came up. The trouble is things are going to get a little bit more complicated. So here we go. If we were to differentiate this, what are we going to have to do?
First,
Make it an explicit function. So we're going to have y squared equals, oops, I guess I didn't need that root sign yet. Y squared, let me try again. Y squared equals negative x squared plus 25. And then I'm going to square root both sides. So if we were to differentiate this, what would this look like?
What we first have trace equal fraction.
Yeah, we wouldn't leave it as a root, right? So we'd end up with two equations, and maybe it's better that we deal with them as two. We're going to deal with the positive stream here, and we'll deal with the negative stream there. So this would be y prime equals negative 1/2. Sorry, you guys can't see that. To the negative 1/2. And then this side would be, sorry, that'd be positive. This one would be negative 1/2 x squared plus. So no real change there, but we would have to change it to.
But wouldn't it be y prime?
Oh, sorry. Yep.
Isn't that the chain rule?
Pardon?
Isn't it the chain rule?
Ooh. Yeah. We would have to do the chain rule there. You're right. We would have to do the chain rule. Okay. I didn't use an erasable pen. Let's go and do the chain rule. I'm going to use an erasable pen now. I've learned my lesson. Okay, so we know that our original function, my outside function is going to be x to the 1/2. And I'm going to add in the plus minus later. And my inside function is going to be negative x squared plus 25. Ooh, I'm trying to squeeze that onto the page there. So k prime x is equal to 1/2 minus negative 1/2, and b prime okay, so the chain rule says is going to be the derivative of this, so 1/2, and we put in the original of this, so negative x squared plus 25 to the exponent negative 1/2 times by negative 2x. Oh, and this has to be a plus minus in front because that would have been what our original one would have been, because it has the plus minus. We need both sides. So if we do this math, I'm just gonna bring that forward. So we're gonna have plus minus negative x times negative x squared plus 25 to the negative 1/2. So that was yesterday's lesson. That was the chain rule. All right. So now, here we go. Oh, I'll give you guys a second to get that copy down. Okay, so this bottom part here, this is where things get things get a little confusing with the notation. And I find it confusing too as I go through it. So when we're doing implicit differentiation, that means that we're not given an x in the equation, we're only given y. So things get a little bit more complicated. So differentiating an expression with respects to x, the u is the original function. So we would differentiate the original function using our D3 rules, even though we don't have x's. And then we're going to multiply it by, if you guys remember that this was a different way of saying like y prime or f prime, f of x prime, like, so it's, this statement here is the derivative. That's just another way, like we flipped way back to, I don't know, was it lesson 2 or lesson 3? There was different ways we can write it. So what we have to do is anytime that we are doing something without an x in it and we're differentiating it, we end up having to multiply it by the y prime. And it's kind of weird and it feels a little different, but that's what we're going to do. Option 2 would be to differentiate both sides of an equation with respect to x using your differentiation rules, which is what we did up here in that one. So this is how we're going to do this. We're going to say let u equal y cubed. Okay, so we're just, that's the original function. There's no x's in it. Okay, so with respect to x, where y is a function of x, but you're not given the equation. You're just giving this part. And it should say differentiate. It says different. That's not what. Uh-huh. There we go. I wrote it in just to make myself feel better. Okay, so this is what we do. This is the notation. D of u, but we said u was y cubed in respects to x. So we're filling this in here. And then we are going to, actually no, let's just use the u in here. Oops, forgot my stick on it. So this is going to be differentiating in respects to x, but for the first time we have no x, so we're doing y cubed, and we're going to times it by dy over dx. So we're going to use our D3 rules here. So what would that look like? 3y squared. And then you're going to follow up with the differentiation, or the derivative of y. So we're going to times that by y prime. And we're not going to leave it as dy over dx because the variable we're using is y. So we're always going to follow up with the y prime. We're multiplying it by the y prime. It doesn't really make a ton of sense, the notation of it. We will get better at it. And you'll see when we move on to the other ones, it hopefully will make a little bit more sense why we use it. Okay, so we're going to do the exact same thing with this one. So du over dx equals 3y to the exponent of 4. Oops. I need to make a statement here. Let u equal 3y to the exponent of 4. We're going to differentiate this just like we used our rules in D3. So this is going to be 12y cubed times by y prime. Okay, so we're going back to that equation that we've seen before, and it's saying, hey, determine the derivative of it. And then part B says determine the equation of the tangent line. What were you doing? Were you on reels? All right, so we're going to do this one. We're going to do this one the exact same way we didn't, like, don't do it the way we did before. We're going to do it using this implicit differentiation. Okay, so what we're going to do is we are going to take the derivative of one side. So we're going to take the derivative of x squared plus y squared. Oops. And we have to take the derivative of both sides. So all we're saying is we're taking the derivative of both sides.
A is done, or?
No, 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 you silly, silly. We have more math to do. Wouldn't that be nice if it was just done? So I broke apart the left-hand side, and we're differentiating in respects to x. So this one's nice and easy. This is our D3 rules. It's all about x. There's an x in it. It's straightforward. So it's 2x, right? Easy peasy. Now this one, because we're differentiating in respects to x, but there's no x in it, we apply the rules, so 2y, but we have to finish up with a y prime. Just like we did up here. We finished with that dy of dx. And when we do the derivative of a constant, what's the value of it? 0. So now what we can do is we can rearrange this equation to equal the derivative. And this is the derivative. So I'm going to have 2y prime equals negative 2x, divide by 2y, divide by 2y. So y prime is equal to negative 2x over 2y.
And then you murder the two, so you just end up with negative xy, right?
Yeah. Right? Nice and easy. So this is the derivative of that we ended up having to do the chain rule for, that ended up being really ugly, but it simplifies. If we do it the implicit way, it's going to simplify to this. So now we're going to do part B and determine the equation of the tangent line at the circle at 4, 3. So what do we need to do? What is really the derivative? It's just the slope, right? So we know that the slope of the tangent line is equal to negative x over y. So we can substitute our values in. So negative 4 over 3. So the slope is 4 over 3. Oh, sorry. Thank you. So implicit differentiation makes it a little bit easier. Where did my... Oh, my clock's there. Sorry. Lost a clock and I didn't know it. So we haven't done the equation yet of the lines.
Why did the clock get over there?
It's been over there for months. But I just looked up and I was like, where's my clock? So again, we're just going to substitute those values in the right places. And solve for the y-intercept. So the equation of the line is going to be y equals positive 4/3 x plus 25 over 3. And that's the equation of the line. Okay, we're ready to keep going? You with me? Yeah. Okay, so we're determining the derivative of this one. So again, we could do the rearranging. That is a strategy to do it, but it gets a little bit cumbersome and it doesn't give us the most simplified term. This is what I would do. And you might like it, you might not like it. I would use the implicit differentiation. And this is how I set mine up, just to keep me... Now remember that everything is in terms of x. So I've got an x squared, I've got a 3y squared, I have an x, I have a minus 4y, oops, I'm running out of room, and I have a 1. So this is how I do it. Again, we're deriving everything in terms of x, so I'm just going to use my rules. So this is going to be 2x. This one's going to be 6y, because that's my rules, but I have to times it by a y prime, because there's no x in this one. This is going to be 1. This one's going to be negative 4 times y prime. And when we take the derivative of a constant, it's 0.
This one's so much better than the other one.
Is it?
Well, now it is.
So we have 2 y primes, you can see that, but we can't combine those terms because this is a coefficient of 6y, this one has a coefficient of 4y. So we're going to treat it kind of like logarithms. We're going to put all the y primes on one side and everything else on the other side, and we're going to common factor that out. So, Dalen, are you good? That didn't sound super confident.
No, not really.
Okay. Okay. Okay, so I'm going to common factor out a y prime here, and I'm left with 6y minus 4 equals negative 2x minus 1. And I'm running out of room, and I'm writing very crookedly. So we know that y prime is going to be equal to negative 2x minus 1 over 6y minus 4. So the difference with this one and everything that we've done is we're setting it equal to y prime, which is awesome. That's our derivative. We feel comfortable with that. But our answer is going to have both the x and the y in it. And we never had that before, but that's what happens is you're going to end up with both x and y in these ones. Okay, you guys do, no, we should do this one together. Okay, so we're going to set this one up similar to what we just did. So I've got the term, and you don't have to do it this way if this is not what you like. This just helped me keep it kind of organized in my brain. So I have 3xy squared, and then I have negative 2y cubed, negative 4x, and a 2. All right, I'm going to do the back end of this table first because this requires the product rule. This one's nice and easy. This is negative 6y squared times y prime. This one is negative 4, and that's 0. Okay, do you guys remember the product rule? Maybe, possibly? Okay. So f of x would be the 3x. G of x would be the y squared. So if I do the derivative of this, it's just going to be 3. And if I do the derivative of this one, it's going to be 2y times y prime. So now the rule was f of x times g prime plus g of x times f prime of x. And I might have got those switched up in the different orders, but it's multiplying and adding, so it doesn't matter what order I do it in. So the derivative here is going to be 3x times 2y y prime plus y squared times 3. Multiplying is harder than you think. So the derivative here is 6xy, y prime, plus 3y squared. Okay, so we needed all this math just to do that part of the table. That?
Yeah.
Okay, awesome. All right. So now we're going to do the derivative of this thing. So we've got 6xy, y prime, plus 3y squared, minus 6y squared, y prime, minus 4 equals 0. Ooh, I went right off the page there. And we're going to use the exact same strategy again. We're going to get anything with a y prime to one side, and just like we did with logarithms, right, when we had that x. So we're going to have 6y prime, 6xy, y prime, minus 6y squared, y prime, equals 4 minus 3y squared. Okay, so now we're going to common factor at that y prime. I know there are other things that are common, like you could take out a y, you could take out a 6, you could take out all of those things, but really what I'm trying to do is isolate the y prime. So even if you took them out, we're going to end up having to move them to the other side anyway. So the best thing is just to common factor that y prime out. So 6xy, 6 squared.
Focus on one thing and absolutely get rid of it.
Exactly. Actually, I'm not going to show that step. So that would be the derivative of that particular function using implicit differentiation. So I find implicit easier than trying to rearrange some of the equations, because now you've got cube roots, you've got y squareds, like all of a sudden it becomes very cumbersome when you have multiple powers on the y. Okay, so now we're going to take it one more step. We're going to do the second derivative for the last example. And tomorrow we're going to have a work period, right? I said I was going to switch those around, but I forgot to put them on the calendar. Okay, here we go. So the first thing that we have to do is we have to do the first derivative. So I'm going to use my table again. Luckily, there's not that many terms. And none of them are combined, which is even better. So anytime I differentiate a y, it's got to be followed by y prime.
Why do you have the 4 in there?
What?
It says yn equals to 4x4.
That's not an n, that's a double, that's the double derivative, that's the double prime.
Oh. Oh, okay.
So it's all fine and dandy. That one was super easy to do. Oh, sorry, I missed a negative. When I moved it over, I didn't make it negative. So that one was super simple to do. That one wouldn't be a challenge at all, but the next layer is a challenge. That's the quotient rule. So now we want to do the second derivative. So really what we're doing is we're taking the derivative of the first derivative. Now I'm going to pop open. Do you guys know that there is a formula sheet at the beginning of every one of your units? So if you ever lose your formula sheet, there's one at the beginning of every one. So I'm just going to pop the quotient rule under here for a second. So we start with g of x times by, and this one order matters because we got a subtraction sign. So g of x times by f of x, the derivative of f of x. Okay, so let's break this down. I'm going to say n of x is the numerator, so negative 4x cubed. And if we were to do the prime of that, that would be negative 12x squared. Right, so I'm just looking at the numerator. And then I'm going to do the denominator. And so if I do the derivative of the denominator in terms of x, that's going to be 6y, y prime. Everybody good with that? I like to get that done before I actually put it into the format. So that's G.
And now we chuck it into the.
Yep. So you got to chuck it into the quotient rule. So this one's going to be y prime prime, because we're doing the second derivative. G of x goes in first, which was my denominator, so that's going to be 3y squared times by negative 12x squared. Subtract the original numerator, so negative 4x cubed, times by the g of x derivative, so the denominator derivative, 6y, y prime, all over 3y squared squared. Maybe let's tighten that up. I think we can tighten it up a little bit. So we are going to have, and I'm just going to tighten it up in this way, like 36x squared, y squared, negative, like just to make it look a little bit nicer. And then I have a subtract and negative, so that's going to be plus 24x cubed y prime all over 9y to the exponent 4. It's not too terrible. The only thing that you have to remember is that if you were derivating y, it always has to end. You still use the same rules as D3, it just has to end with the y prime. Because it's in terms of x, but there was no x in it, so this is how we kind of get around it. And it makes it a little bit easier. Again, it's just taking your time and going through the steps. All right. That's it, that's all.